Hello everyone. In this lecture, I'm going to introduce the Bernoulli equation, which is a special form of the momentum equation, the um, uh, Euler's equation that we investigated, and it's a very well known and widely used formula and equation in fluid mechanics, especially in engineering problems. So Bernoulli equation is a special form of the momentum equation, which describes the dynamics of the flows. So it's kind of a simpler form of the Euler's equation for steady, inviscid, irrotational, and constant density flows. So let's investigate them one by one. So the conditions for the Bernoulli equations are as follows. First, the flow has to be inviscid. So we are investigating an inviscid flow. Inviscid. And by inviscid means that viscosity or F viscous force is 0, right? So it's kind of similar to this Euler's equation where we didn't have viscosity. So the viscous term here is also 0, right? And now the second condition is constant density. So we assume that the flow has a constant density. So it's not just incompressible, but also the density is constant. So this means that rho is constant. So it's incompressible, but also the density is constant. So because the density is constant, I can rewrite this equation as follows. So this is the Euler's equation, right? So because the density is constant, I can put it into, I can divide the whole thing by rho. So let's divide it by rho. So here we have minus grad P. So let's see, I can write it as this. So I can write it as, so we had plus G, right? So I can write it minus grad P over rho. And because rho is constant, I can take it into the gradient. Gradient, remember gradient is like a differentiation. So because rho is constant, I can write it as follows, as this. We assume rho is constant. So this is going to be our momentum equation, because for a constant density fluid. And then the third condition we have to write to drive the Bernoulli equation is that the flow should be steady. So we are only investigating steady flows for Bernoulli equation. And what does this entail is as follows. So steadiness means that the material derivative of velocity dv over dt, or d over dv over dt, which equals to partial v or partial t plus v dot grad v. Because this is constant, because this is steady, this term should be 0, right? So we only have this term for the left-hand side of the momentum equation. And we have, this is, and this is a mathematical identity. We can write this as follows, the second term. So we can write v dot grad v. You can show and prove that this equals to grad v squared over 2 minus v cross grad cross v, or v cross curl of v. And this is a mathematical identity that you can show it. You can show okay for vectors. This is something that is a mathematical identity. So I'm going to use this identity and then rewrite the equation for the Euler's equation. Okay. So the left, because now we have this steadiness assumption. So this means that this term, and I'm also going to use that, so it's as follows: grad v squared over 2 minus v curl of v cross curl of v. Again, this is, we call this curl of v. Okay, just so you remember what I mean by curl, equals to the right hand side, which is here, so I'm just going to write it down, minus grad p over rho plus g. Okay, so this is the steadiness assumption which leads to this. And finally, the last assumption that we have is the flow is irrotational, meaning it doesn't rotate. So if the flow is irrotational, vorticity, which we define it as omega, is a vector, which is curl of v this is just a definition of vorticity, is gonna be 0. So we don't have any vorticity, we don't have any rotation. This is what it means by irrotational. It means that the curl of velocity should be 0. Okay. So now that we have this, I'm going to define one more thing and then rewrite the last Euler simplified form of the Euler's equation again. So we define potential function as follows. So we define it, we can rewrite g, which is a vector, as scalar g, this is just a number, right? Like 9.8 multiplied by gradient of h, and we define h as potential function, which is literally just height or altitude. So grad h is, for example, the partial h over partial x in the I direction is a vector, right? Plus partial h over partial y in the j direction, and partial h over partial z in the k direction. Okay, so this is literally just we define this potential function and rewrite the weight of the fluid, or the g, or the gravitational constant vector, as a scalar g times grad h. Okay, so now that I have this, I can rewrite this equation. So let me rewrite it here. So we have here this, and because we assume that the flow is irrotational, so this term is going to be 0, right? So this is 0. And instead of g, I write minus g grad h. Okay. Now that I have this, I can rearrange the terms and I get this grad of the gradient of this quantity v squared over 2 plus p over rho plus gh. Again, g is a constant. I can take it into the gradient, right? It's gonna be a constant, so I can take it inside that. So it's gonna be gh. This equals to 0. Okay, an interesting formula that we got by just these 4 assumptions that we made for the Euler's equation. Okay? So now say you have a particle that flows inside a flow like this, and this has a streamline like this. This is the velocity, and it has a streamline like this, okay? Okay, so now what I'm going to do is I'm going to integrate this gradient along a streamline. Okay, so I'm going to integrate this gradient along streamline. This is a streamline. Just again, I'm going to write it down. Streamline. So along streamline, I'm going to integrate this quantity v squared over 2 plus p over rho plus gh, okay, and then dot dl, okay. I'm going to multiply it by dl, so say l is, you can get a, you can have a origin like here, and then this is gonna be your L, and so dl is just you dot it with the L, and inner product it with L, and this equals to what? This equals to 0. The integral of 0 over there. So this means that v squared over 2 plus p over rho plus gh equals to constant, right? If you integrate it, this should equal to a constant along a streamline. And this is a very important formula. And this is actually Bernoulli equation. Just remember, if you integrate across a streamline, not along a streamline, then this term that we said is 0 is not necessarily 0. is not necessarily zero. Okay, so that's why we are taking the integral over a streamline. And you can show that this term is going to be zero. It's not that difficult if you take this integral along a streamline. Okay, so I'm not going to show it here, but this is generally how it should be here. It's a simple thing to show that this term is going to be zero along the streamline. So if you have a steady flow, you will have something like this. Say this is your velocity. So you can show that this is gonna be zero if you go along the streamline. Okay, if you follow a path along a streamline, flow a streamline, this quantity is going to be zero. So I'm not going to show it, but this is just I wanted to say why did we take the integral or across like along the streamline, not across streamlines. So for example, we don't take the integral in this direction, something that is across the streamline, but we take it along it. Okay. So now, since rho is constant, we can also write the Bernoulli equation. We can just multiply it by rho and write another form of Bernoulli equation, which is 1 over 2 rho v squared plus p plus rho gh equals to constant. And this has an interesting meaning and interpretation. So just look at this. If you remember from your physics, 1/2 mv squared, right? This was, we call that kinetic energy, right? So this is like kinetic energy. And this term, like mgh from your physics, you might also remember, this is potential energy. So what does this tell us? Bernoulli equation says that sum of kinetic energy plus potential energy is constant along a streamline of a flow when there is no energy loss due to viscosity, right? So we assume that we don't have any forces, any viscous forces. So when we don't have any viscous forces, the sum of the potential and kinetic energy of the flow is going to be constant, and that is exactly what Bernoulli equation states. Okay. So now I want to show an example, it's like a simple example of this Bernoulli equation, and then a little bit trickier example in the second session. So I want to talk about stagnation pressure. What does that mean? So say we have a bluff body here, like a cylinder or anything. And then we have the flow that is going around this. So here the flow goes around it. At this point, the flow is gonna stop. It's not gonna move, right? So I'm gonna call this O. And then here, say we are looking at this streamline, okay? So here I write it as Z infinity, like it's very far from the bluff body. So I'm just gonna write it, the elevation of it is Z infinity, its velocity is V infinity, and its pressure is P infinity. Okay, it's just far, very far from that. So let's write the Bernoulli equation for this bluff body, for the flow around this bluff body. Let me write it this way. For the flow around this bluff body. Okay, so along the streamline infinity to O, we can write the Bernoulli equation as follows. So what was the Bernoulli equation? We have it here. Along this streamline, this is constant, right? So I can write it as follows. So rho V infinity plus P infinity plus rho G Z infinity equals to P, let me write it this way, one half rho V0 or VO square plus P naught plus rho GZ naught. And we know this streamline Z infinity equals to Z0, and V here in the stagnation point is 0, right? It's not moving, it's just, the flow is just stuck there. So the Bernoulli equation simplifies as follows: P infinity plus 1/2 rho V infinity square equals to P0. And P0 is actually what we call as stagnation pressure. The pressure at the stagnation point, where it is maximum pressure in this flow. Maximum pressure. And this equals to, at any point that you take along this streamline, so not just P infinity, we can write it, the pressure, it equals to the pressure at that point plus 1/2 of rho V square, any point in this streamline. Okay, for any point along this streamline, we can write it like this. So I can write this as follows: P minus P infinity, pressure at any point, minus the pressure in the infinity, very far from the bluff body, equals to the difference between pressure is the difference between square of the velocities, V infinity minus V square. Okay. I can rearrange these terms as follows: P minus P infinity by dividing by 1/2 rho V infinity square of both sides. So I'm going to get 1 minus V over V infinity square. Okay. So based on this, I am defining a pressure coefficient. Pressure coefficient as follows. So I define Cp, or pressure coefficient, equals to P minus P infinity over 1/2 rho V infinity square. So this numerator is, we call it static pressure. The denominator, we call this as dynamic pressure. So it's also a pressure. And why it's pressure? Because the units have to be the same. So this is also has a unit of pressure. So this, we call it the dynamic pressure, which depends on the velocity. Okay, so say if your velocity is 0, then that means your dynamic pressure is 0. But if your velocity is very high, then it means your dynamic pressure is high, but then your static pressure is going to be lower. Okay, so now I want to divide the Bernoulli equation similar to this pressure coefficient by 1/2 rho V infinity square, and then non-dimensionalize all the terms in this Bernoulli equation. Okay, so let's divide Bernoulli by 1/2 rho V infinity square to non-dimensionalize all its terms. So this is Bernoulli, just so you know. So I'm going to divide all the terms. So this is for the whole thing. So let me rewrite the Bernoulli equation. It's 1/2 rho V squared plus P plus rho GH equals to constant. So let's divide everything by 1 rho V infinity squared. So the first term is going to give me V over V infinity squared. So it's, again, this is a non-dimensional term, right? V over V infinity, velocity over velocity, is non-dimensional, hasn't any dimension, or it's a scalar, it's just a number. P over 1/2 rho V infinity squared, and then GH over V infinity squared. So this equals a constant. Okay, so let's see what we call. So this is just speed ratio, right? Speed ratio. This is again static pressure over dynamic pressure, or pressure ratio, right? And this one, we call this Williams number. It's a non-dimensional number. Is similar to Freud number. So if you remember from your undergrad fluid mechanics, Freud number is V over square root of GH. So this one is kind of 1 over Freud square. So it's called Williams number. So this is also a non-dimensional form of the Bernoulli's equation, and you can non-dimensionalize it by different terms and write it and interpret it differently. So I just showed one interpretation of it in terms of kinetic and potential energy. You can show it as pressure head. And this is another way for non-dimensionalizing it using velocity components. Okay, so in the next session, I'm going to solve one example of this Bernoulli equation for finding the force that is applied to a nozzle.